We are now going to apply this external diffusion concepts specifically to first order elementary reactions. So it's very important that you tune your minds to this is only applicable for first order systems, and that you recognize what should happen and where we start to deviate when we consider higher order reacting systems. Of course, here the order refers to the true order of my reaction. So if before theme 6, if we have the mass-based rate and we have A goes to B and it's elementary, we could write that it's Ki dash times Ca. But now, since I have external diffusion limitations, there must first be a flux of that component to my catalytically active surface, and the concentration I must substitute here is actually the surface concentration. If I want steady state conditions, we proved in the previous part of this theme that we must ensure then that these two rates are equal. So the rate at which it diffuses to the surface must be equal to the rate at which it gets consumed if I want a steady CAS value at that surface of my catalyst particle. Because it's first order, and only because it is first order, I can actually get an explicit equation from this equation that I derived in the previous slide section for Ca surface as a function of Ca bulk. This is very convenient because we cannot measure Ca surface, but we can measure the bulk phase concentration. This is something that we can take a sample of and we can measure it. So we would like to express our variables in terms of the bulk phase concentration. So now we can manipulate our rate equation, that's in terms of Ca surface, by replacing it with this whole group of variables over here. So you will see that the green line now says this is actually Ca surface. Ca surface, it's the rate parameter, the Ki dash, multiplied by Ca surface. But I could write Ca surface in terms of the rate constant for external diffusion and the rate constant at which the intrinsic reaction actually occurs. And now I separate, once again, everything that looks like a K value from everything that looks like a concentration value. And I can see that I can make up a new group of terms. I can group all my rate parameters together and say, all right, I've got a modified rate equation that I can multiply with Ca bulk. And that will also give me this surface concentration rate. And we call this rate parameter, this rate constant, our effective rate constant. This is the rate constant that I will actually observe if I measure my rate based on the bulk phase concentration and I want to calculate that rate constant. It will be an effective value and it will consist of this grouping of both my other two rate constants. Due to my steady state condition, I can now once again realize that I've got the intrinsic rate at which the reaction reacts, rate order equal to 1, surface concentration needed. It must be equal to the rate of diffusion. And after I have now substituted Ca surface in terms of Ca bulk and all my rate parameters in my rate constant, that effective rate constant multiplied by Ca bulk must give me exactly the same value for the rate, and in this case my rate is calculated in moles per kilogram catalyst per second. It is very convenient to describe these series processes rather as a series of resistances rather than rate constants. So in order to do that, I manipulate my rate equation to say I want to write it as a driving force divided by a resistance. So this is the resultant equation that I've come up here. So the driving force, this is an analogous to what we get in electrical currents. The driving force is your voltage. The resistance, so V divided by R, will give me the current. And in this case, the driving force, the bulk phase concentration, is the ultimate driving force of how fast both rate processes can occur, divided by the overall resistance, which is a sum of resistances, will give me the rate or the current at which my reaction rate can actually take place. you can now unpack this, and I leave the proof to the listener or the reader, to see that I can actually write 1 over K effective. So if I should take this whole equation and I should take its inverse, I can write it as the resistance due to the external diffusion plus the resistance due to the actual surface reaction rate. And the resistance means it is 1 over the rate constant, 1 over the rate constant. In other words, a very high resistance will mean that I've got a very small rate constant. And if I've got a very high resistance to external diffusion, it means I've got a very small rate constant that drives that external diffusion process. It is very important to notice that the surface concentration here, after it diffused through my viscous sublayer, it's got limiting boundaries within which it must fall. It cannot go larger than the bulk phase concentration. In the limiting scenario in the upper end, the surface concentration will in fact be equal to the bulk phase concentration. That's the highest it can go. And on the other end, other limiting scenario is that the surface concentration cannot go lower than 0. It must be somewhere within these bounds. So we are first going to analyze limiting scenario number 1. And that is the scenario where the transport through this boundary layer is very fast. So external diffusion is a very fast process. And when is it fast or when is it slow? I know I'm going to get that question. And of course, that all depends on the relative size of your Ki dash versus KCAM. If Ki dash is 1 times 10 to the power of minus 9, and KCAM is equal to 100. 1 divided by 100 is going to be pretty much negligible compared to 1 divided by 1 times 10 to the minus whatever I previously mentioned. So in this limiting case, where this is a very fast rate, so KCAM is fast, then the resistance to external diffusion is low. So this goes to 0 compared to that term, meaning that my effective resistance or my effective rate constant becomes pretty much equal to Ki dash. So in my rate equation, I can say that my RA is equal to the effective rate constant times Ca bulk. And in this limiting scenario, K effective simply becomes equal to Ki dash. That is when my KCAM is very large compared to my Ki dash. If I consider my steady state equality of the rates that must hold, what this implies is that KCAM becomes really large, so that this driving force can pretty much go to 0 and I will still be able to maintain that same rate. And if this driving force goes to 0, it implies that the difference between Ca bulk and Ca surface becomes negligible. And that denotes the one limiting case where the reaction rate step controls the rate completely. Also, we can state that external diffusion does not influence the rate, or it has no impact on the rate. So I can make my catalyst particles smaller, I can stir faster, I can flow faster. That is not going to affect my rate anymore, because this rate constant over here is already large enough not to matter. It is already equal to 0.00001 plus a million. And if I make it smaller, it's going to be 0.0000001 plus a million. You are going to waste your effort by making this resistance, trying to make this resistance smaller by changing stuff in your reactor. In the other extreme, I have the scenario where this transfer process, as it diffuses through this boundary layer, is very slow. A slow rate is indicated by a very small rate constant. So if this becomes really small, the resistance due to this rate constant starts to dominate whatever I observe in my reactor. So it becomes a forms a bigger and a bigger and a bigger part of my overall resistance. Up till the point where it is so big that this becomes 1 divided by 1 times 10 to the power of minus 9. This is 1 divided by 100. And once again, comparably, I can say that this resistance can be neglected. So what happens here is that as I approach this scenario, the difference between Ca bulk and Ca surface must go up in order for that rate to remain under steady state conditions. If this goes up, I end up at the limiting scenario where the surface concentration over here actually goes to 0. So what that implies is the stuff diffuses through very slowly, and there is a waiting catalyst active site there. As soon as it reaches it, it reacts and it disappears. And then another molecule comes through, it diffuses through, and as soon as it hits that surface, it reacts and it disappears. And in this case, this limiting scenario, where I have a very small external diffusion coefficient, very high resistance to external diffusion, we say that external mass transfer controls the rate, not only affects or impacts the rate. That is when Ca bulk is larger than Ca surface for all those scenarios. Then it affects or it impacts the rate. But when it controls the rate completely, it means that the surface, it's so slow that the surface concentration pretty much goes equal to 0. It also implies that since this thing becomes negligible in comparison to the other resistance, I can write my rate expression as a function of only my external mass transfer constant, because that then simply becomes equal to my effective rate constant. You can think about the two different scenarios as you sitting in a restaurant and you have got a plate in front of you and you ordered some chips. And in one scenario, the waitress, which is the transport process, waitress or waitron, brings you one chip and then goes back to the kitchen. And then wait a minute and brings you another chip and goes back to the kitchen. And as she puts the chip down on your plate, you immediately gobble it up. So that chip immediately disappears. So your plate, for all practical purposes, remains empty of chips. In another scenario, she immediately brings you a full plate of chips. Immediately brings you a full plate of chips. And as soon as you completed that full plate of chips, there's another plate of chips ready. So the rate at which the chip disappears depends on the rate at which you, as the catalyst particles, can eat it and subsequently convert it to energy and some byproducts. So what is now true for non-first order reaction systems? What is different in our analysis? And it's actually only the math. For our multiple order, any order rate equation, I can still equate the two rates, the mass transfer rate, and here just to show you a different example, I use the volumetric based rate constant and the volumetric therefore correction factor for Kc to express my rate on a per volume reactor basis. They must still be equal to each other. And therefore I can still find an expression for CAS. However, due to the non-linear nature of that equation, I can have multiple solutions for Ca surface. So I can have value 1 and I can have value 2. However, what I must realize is because of the boundaries in which CAS must fall, there will only be one legal value for my surface concentration. I can still use that approach. What is illegal? What is illegal is this equation where I can write it nicely in terms of my resistances in a row or my ducts in a row. This does not apply. The concept of an effective rate constant does not apply for higher order reactions. If you use this anywhere in CRO, it is immediate suicide in terms of your marks. So your marks will suddenly just all disappear if you apply the effective rate constant phenomena to higher order reaction systems. However, what is true is the empty chips plate and the full chips plate kind of analogy that we can draw. We can once again say if KCAC in this case becomes really large, I get the scenario where the bulk phase concentration approaches the surface concentration. So that's that full plate of chips. I get delivered my full plate of chips, and the rate at which I eat it just depends at the rate at which that surface concentration can take place. That is if I have very large values for my area-based rate constant of external diffusion. On the other hand, of course, I can once again have the empty plate scenario where I get delivered one chip at a time and I just, as soon as it lands on my plate, I eat it. So that is when this rate constant compared to the rate at which the reaction rate takes place is very slow. The rate of delivery, the service is very poor compared to the rate at which I can eat. So as soon as it ends up in my plate, I consume it. So once again, that scenario says the surface concentration pretty much goes to zero. Surface concentration pretty much goes to zero. So what happens here is if I consider this rate equation, this is a very interesting phenomena that is going to occur. Sorry, there's a negative sign missing there. The rate at which the stuff can disappear, if I then consider the mass transfer based rate. So Ci surface becomes equal to zero. So this is pretty much minus zero, which if you should measure that rate and you just measure the bulk phase concentration, it will appear as if you've got a first order rate expression, regardless of the actual true order of your reaction system. So what that means is this rate, if you have this kind of scenario where external diffusion completely controls your rate, I cannot actually measure my true rate order because I cannot see how fast can I eat depending on the amount. Does the amount of chips in my plate affect the rate at which I can eat? Because it will always appear to be for first order. So this is a masking kind of scenario where the Ci surface concentration goes to zero because of the slow rate of delivery, where all reactions will appear to be first order regardless of their inherent nature is actually of a higher order. Another question that always pops up is, okay, that's fine if I now have a very nice rate equation where I only have one component that describes my rate. But what if rate equations that's more complicated, like Ca, Cb, or even more so? What you will do is you need one of the reactants will be the limiting factor. So you will have to calculate the diffusivity or find the diffusivity of each of the components. And the one with the lowest diffusivity, for that one you will have to consider the external diffusion process. The other one is going to be able to keep up. So external diffusion will not control the concentration of B, in this case, at the surface. So for component B, if the diffusivity of component B in the mixture is much higher than the diffusivity of component A in the mixture, it means that Cb at the surface will simply be equal to Cb in the bulk phase. But Ca at the surface will be less than Ca in the bulk phase. And of course, vice versa, if I have a very high diffusivity of A compared to B, the scenario is going to be reversed.